So last day, I think I said something like Physics 12 begins. We took what we had done with forces, and up until last day, it was really all a review of Physics 11. I'd snuck all of that in. And we said, what if we tilt things? Well, first of all, the fact that we tilted it, that there was angles, I said we're going to go components. Really the issue was, what's the best way to go components? And I argued with you, I said, I think the best way is to break up gravity, because the rest of your forces will tend to be in line with the hill or perpendicular to the hill. They will already be sort of, you can think of a horizontal and a vertical component, but it's a hill, so I don't like using horizontal and vertical. I use parallel and perpendicular. Normal force will always be perpendicular. Friction will always be parallel to the hill. Let's break up gravity. We'll break up gravity into its parallel and perpendicular components. And I said, this one time, I'm strongly going to recommend that we all draw things the same way. I always draw the perpendicular component first. My abbreviation for perpendicular is upside down capital T. Then I draw the parallel component next. And again, Ty, by parallel, I mean parallel to the hill. Parallel to the hill. My abbreviation for parallel is two parallel lines. Then we proved this once. We said that angle there is the same as that angle up there. And I show that just by coloring in the point of the ramp and coloring in the top of the triangle. That tells me what my opposite and adjacent hypotenuse are. And we did notice that MG parallel was signed. By the way, if you blank out on it, you could, even from this picture here, you might notice that parallel is opposite. MG is hypotenuse, opposite hypotenuse. It is sine. And then if parallel, two lines was sine, what was perpendicular? Of course it was cos. After that, all of our winner minus loser stuff, all of our friction is mu times the normal force, look, all works. But Drake, I have to be, I think, way more careful. And I'm going to say to you, just be way more careful. But I'll show you some of the questions that we can handle. So we did example 7. We finished off with example 7. This one here, after example 7, where I wrote pause here. Oh, I didn't want to hit that button. Wrong button. Says this. I guess this would be example 8, but I didn't put a number on there. A block remains motionless on a surface that's inclined at an angle of 21 degrees. What's the minimum coefficient of friction on the surface? Why minimum? You know what? This will assume that it's just ready to slide down. There could be plenty of breathing room. Maybe the coefficient of friction is way bigger. Let's pretend that, hey, if it was a car, maybe this car is perfectly safe on the hill, not ready to slide down. But we'll find the minimum. I think to start out, I'm going to dulp. And for these questions, for any ramp question, if they don't give me the ramp, I am going to draw a little picture. I'm going to draw my ramp pointing to the right. Why? Well, I'm just used to things moving to the right. No good reason beyond that. Here's what I would advise. I'm not going to draw my ramp like this big and think that'll draw a half decent sized picture. Got notes okay? You pick up your pencil? Hey, there we go. Block. Right there. If you want to label it with the 7.5 kilograms, you can. I tend not to because it clutters up the rest of my diagram, and I've got it sitting in the question. Right angle, 21 degrees, that angle there. Which way does this block want to slide? And don't say down the ramp. Okay, so I'm going to kind of note that. Let's label our forces. What are the forces acting on this block? Get the obvious one. Okay. I told you last day I tend to draw my MG line nice and big because I want to be able to see that triangle, and I always put the MG on the same side as the pointy part. Speaking of pointy part, here we go. Let's see. Let's pause the video lesson. And although normally I would tell you get the next force and the next force, for ramp question I always pause and I say I better break up gravity. I'm going to break gravity up into the perpendicular component, which I guess is going to be about that far. MG perpendicular. And the parallel component, mg parallel. And Julie, I strongly encourage you, put your vector lines on the put the arrows on the vector lines. Especially that bottom one, the parallel one, because it tells you which way this thing wants to slide. What other forces are acting on this? Are we on a surface? Then there's going to be a normal force. I've always said, is it sinking into the ground like quicksand? Is it flying into like Superman? Really what I mean is, now, a couple of days ago I said all of your up forces equal all of your down forces. Everything up equals everything down. We're slanty. What I'm going to say is there is going to be a normal force. How big is it? The same size as the perpendicular component. I might have drawn mine a tiny bit too long. I think I did. About like that. Is there friction in this question? If there wasn't, those two blue lines would be the free body diagram. On your test, almost certainly as a multiple choice question, I will give you a situation and then I'll say, pick the best free body diagram from these four options. So please remember, for a free body diagram, components don't show up. Those red lines, those red dotted lines, would not be on the free body diagram. I put them on to do the math, to do the physics. Is there friction in this question? Yes? Which way? Which way does this block want to slide? So which way is friction acting? In fact, since this is at rest, if I was really clever, and I wouldn't take marks off, but if I was really clever, I would draw friction the same length as mg parallel, because those are canceling each other out. It says it's at rest. Well, it says motionless. You got it?
Yeah.
Okay. We're right after example 7. Who's winning? Well, it's sort of a trick question. It's a tie. If you wanted to completely use winner minus loser, you might say the parallel component of gravity is pulling down. Friction is in the opposite direction, pushing up. But it equals 0 because you're at rest. Or, Liam, if you were really clever, you would have said, it's a tie. What could I do with that negative friction? Plus it to the other side. And so if you said, hey, Mr. Duick, I went straight to saying that, I would say, nice, I'm good with that too. All right. mg parallel equals, friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. And it ain't mg! That's physics 11. What is it this time? Okay, so I'm going to get mg perpendicular. mg parallel equals mu mg perpendicular. Mr. Duick, will the masses cancel? I think they will. You could cancel them on this line if you want to, or you can cancel them on the next line when you bring in the trig. I don't care. I usually cancel it on the next line because that seems to be less intimidating to the students, but I'm telling you the m's are going to cancel. mg parallel, g parallel, g two lines. Sine? So you're saying it's going to be mg sine theta? mg two lines? Sine. It's sine. No, now I'm going to do the right-hand side. You know where I'm going to do the right-hand side? On the right-hand side. Because I did the left-hand side on the left-hand side. So now I'm going to do, Connor, the right-hand side. There's going to be a mu. What's mu? I don't know what's mu with you. An m. A g. Doesn't vanish. Connor, perpendicular, which trig function? Of course it is. And I'm doing this algebraically, not putting in any numbers yet. I'm looking for interesting patterns. Something kind of cool happens. Is there an m in everything? But something else kind of weird happens. What? Huh? The g cancels? What does that mean? Here's what it means. It means this ramp, if you had Star Trek technology and you beamed it to the moon where G is different, the mass would still be at rest. Or if you beamed it to Venus where G is also different, the mass would still stay at rest. Or to Jupiter, or to Saturn, or to be honest, any other planet in the universe, you wouldn't have to change the angle, or you wouldn't have to change the coefficient of friction to keep it at rest. That mu would be sufficient. This is a universal law. What are we trying to find here? What's mu? I don't know. What's mu with u? How am I going to get the mu, the coefficient of friction, by itself? I'm going to get mu equals Math 12 humans. Have you guys done trig identities yet? Okay. Does anybody know what sine over cosine actually is? Duncan. Tangent. Turns out it's actually tangent. You don't need to know that. It's just kind of nerdily cool. It turns out, because we haven't used tangent much in a while. We used it all the time last unit to find the angle quite often. Here, it turns out if you want to know what your minimum coefficient of friction is on a hill, if you're designing an engineering hill or something like that, it's the tangent of the angle. Hashtag nerd trivia, I guess. Here, I'll type in sine 21 over cos 21. For this block to stay where it is, or for if this is a person standing on a roof and they're wearing sneakers, for them to be able to safely stand on the roof, their sneakers have to have at least a coefficient of friction of 0.384. And by the way, if your sneakers had exactly 0.384, you would feel through your feet really uncomfortable. You may have been in a situation where you feel like you're almost about to slip. You would feel that the whole time if you were walking on this roof line. You would not be a happy camper. If your sneakers had a coefficient of friction of like 0.6, you'd feel, oh, I got good grip on my shoes and I can feel that through my legs. 0.384, what units? Oh, none. Coefficient of friction has no units. It's not a force. It's just how sticky one object is in relation to another object. Okay? I like that question. I like that question. I like that question. Although I would also have no problem having it accelerating and still asking you to find mu. What if it was accelerating down the hill at 2 meters per second squared? What's the minimum coefficient of friction? Example 8. I like example 8. I like example 8. I like example 8. Example 8 is a nice question. Consider a 6 kilogram mass sliding up a rough friction, 32-degree ramp with an initial speed of 20 meters per second. Mr. Dewick, how can it be sliding uphill when don't things slide downhill? Someone gave it a push before we walked into the scene. So someone must have given it a big push and walked away, and now when we're watching it, it's still traveling up the hill at 20 meters per second. Now it's going to slow down. A asks, find the force of friction. B asks, find the acceleration. C asks, find the time to stop. D asks, I guess, find a distance. I like this question, I like this question, I like this question, but Kayla, I would probably just ask you to do part D, knowing that you'd have to find A, B, and C to solve D, and I'd be happy with that. I'd just say, here, how far does it go? You would say, well, D equals question mark. What am I trying to find? And you would have to eventually work your way back towards, I guess, need to find acceleration. How do I find acceleration? You know what? There's friction in the question. I guess I'm going to deal with that too. How am I going to start, folks? Nope. I'm going to draw my ramp right here. Angle is 32 degrees. Pardon me? Can you just do tangent 32 divided by, to find friction? No, that would help you calculate the coefficient of friction, but I've given you the coefficient of friction. This is not the minimum coefficient of friction. This is in fact, this isn't enough to stop it. It's going to keep moving for a while. So sorry. It's moving up the page. You know what? I'm not going to draw that in, but it's moving up the page. Up the ramp. What are the forces acting on it? By the way, I drew it down here just to remind myself that it is moving up. What are the forces acting on it? Get the, for what it's worth, what are they asking me to find? Eventually, they're going to ask me to find that distance there. That's what part D is asking me to find. Did you notice how D is asking you to find D? Did I plan that? Well, okay. What are the forces acting on this? Get the obvious one. Can we say that with a little more authority and confidence in our voice? Okay. I'm going to break that up into its components. It's going to get broken up into a perpendicular component and a parallel. And I can't emphasize this enough. When I say parallel, I mean parallel to the slanty part of the ramp, not parallel to the base. And Robbie, that's a lovely right angle right there. What other forces? Is this sitting on a surface? There's going to be a normal force. How big? That big. Mr. Dueck? What, Kayla? Will the normal force always be the same size as mg perpendicular? No, because I could add other forces, and we will eventually. Oh, what if someone's pushing from above? What if someone's pushing from the side? We can deal with all that. Will it usually be the same size? Unless it's a weird, yucky question, yes. What else? Is there friction? Which way? Wait a minute. Shouldn't friction be up the ramp? Why would it be down the ramp? Ah! The block is moving up the ramp, and friction always acts in the opposite direction of motion. So, friction. Mr. Dueck, it's moving up the ramp, but you don't have any forces pointing up the ramp. How is that possible? Don't you have to have a force pointing up the ramp if your velocity is up the ramp? Force does not tell you velocity. Force tells you acceleration. We're moving up the ramp, but are we speeding up or slowing down? Which way is our acceleration? Down the ramp. Which way is our net force? Down the ramp. It's all good. Okay. Rebecca, what does part A want me to find? Friction is what times what? I don't know the normal force. Oh, but look. I don't know the force the same size as a normal force. It's not mg. Yes? Connor, which trig function is that going to be? Yeah, you. Of course it is. So it's going to be mu mg cos theta. Another thing I was going to mention, common mistakes that I see, in fact, I helped somebody with it earlier today. People forget the g's. I don't know why. Or they'll get G in the first term, but they'll forget to include it in the second term because I guess their brain has reminded them, you already took care of the G. Oh, it showed up later on too. So just be really, I said at the beginning of this lesson, James, raise your level of paranoia. Be uber careful. So friction is going to be 0.1 times 6 times 9.8 cos 32. 0.1 times 6 times 9.8 cos 32. 4.9865. I'll call it 4.99 newtons. Hey Drake, what's B want me to find? Winner minus loser. Who's winning? Who's winning? I don't think friction's the winner. I think there's probably a more dominant force because even without friction, there's something winning. Okay, mg parallel. So the winning direction is going to be down the ramp. Who's losing? A lot of kids want to say friction's a loser because they're so used to friction slowing things down. In this case, though, I think, Drake, we have two winners. Two forces down the ramp, yes? No losers. It's like kindergarten. Everyone's a winner. It's like sports day in elementary school. Everyone gets a ribbon, right? So it's going to be winner plus Winner. Is that okay, Ty? Because they're both pointing. As soon as I decide that this is the winning direction, that's in the winning direction. Plus, they're both pointing down the hill. Drake, what does winner minus loser always equal? Yep. I could, at this stage, if I wanted to, Connor, drop this 4.99 into there. I'm going to do this all algebraically, though, because I'm pretty sure the m is going to cancel later on, and I'll get the a by itself, and that'll end up being less work in the long run. So I'm going to go, Connor, mg parallel, what's 2 lines? So this is going to be mg sine theta plus, I'm going to drop this down right to here, mu mg cos theta. Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. What does that always equal, Drake? Winner minus loser always equals ma. Drake, my friend, is there an m in the first term? Is there an m in this term? Is there an m in this term? Is there an m in everything? That's kind of nice. And in fact, I was trying to find the acceleration. The a is already by itself now. Common mistake. I said this earlier. Kids get the g here. The number of times I'll see kids having written a g, but not type it on their calculator. And I guess it's because their brain remembers typing a 9.8 and thinks they've taken care of it. There's also going to be a 9.8 here. Let's fill in the numbers. It's going to be 9.8 sine 32 plus 0.1 times 9.8 cos 32. And I get 6.02 for, I'll write 6.02, but I'll keep this on my calculator. Is that right, 6.02? Anyone else? Mm-hmm. Yeah? It's an acceleration, meters per second squared. Liam, what's C want me to find? T equals question. Time to what? That tells me something. VF is 0. Did they give me VI? They did? Oh, good. What was VI? Sorry? 20? What else do I need to find T? Oh! What did I find in part B? I'm looking for an equation that has VF, VI, A, and T, and I think this is the one we used the most last year in Physics 11. I think it's VF equals VI plus AT. Get the T by itself. Yeah. I get 0 minus 20 all over 6.02, and I get a problem. When you type that in, what's weird about your time value? Is time ever negative? Okay, so you ready? Here, we went winner minus loser, and when we went winner minus loser, we let down be positive. Yes? But last unit, when you were slowing down, what did we call that kind of an acceleration? So we're going to have to add a negative for part C. We're going to have to go back to our kinematics. Slowing down meant negative. And if you do that, you'll get a fine answer. Or you could just ignore the negative that your time value gave you. So I'm going to go put a negative there, and I'm going to go bracket 0 minus 20 divided by negative answer button. There's my workaround. And that will give me a positive time value of 3.32 seconds. Is that okay? What's D want me to find? I can do this a couple of ways. I could use d equals VIT plus a half AT squared, because I now have time, 3.32. Or I think I could use VF squared equals VI squared plus 2AD equals VF squared minus VI squared all over 2A. Both of those will give you the same answer. In both of them, you are going to have to let A be negative, because they're from our kinematics unit, where slowing down was negative. Since this one already has the D by itself, I'll go with this one. VI, 20. T, 3.32 plus 0.5, negative 6.02, 3.32 squared. Times answer button plus 0.5 times negative 6.02429. I'll carry a few extra sig figs 6 because I happen to have that sitting there. Times answer button squared. VIT plus a half A negative slowing down T squared. And I get 33.2 meters. If you did it using this equation, you would get 0 squared minus 20 squared, all divided by 2 times negative 6.02, and you also get 33.2. We've rounded off differently, but same answer. Which one's right? If I'd asked you part D without using part C, I would have used this method. If I had time, I'd probably use the D equals VIT plus a half AT squared, because the D is already by itself and I'm lazy. Okay. So I had already assigned number 1. I had already assigned number 2. I think you can try number 3. You can try number 4. Five is good. Skip 6. 7 is 7. You know what? Not all of 7. 7b. See if you can write an algebraic expression for acceleration when there's friction sliding downhill. Eight is good, but you can skip A. 9 is pretty tough, but you can handle number 9. Skip 10. 11 is good. Max, if you want to, you can use your shortcut for number 11, because that's, I think, the same as the one that we started class with. I think it'll be tangent, but or you can prove it. 14. And I got a video to show you.